Okay, so I think, Gérard, it is safest if I don't take the control of the screen. I will just speak like this and introduce you, if you don't mind.
Sure, sure.
Yeah. I think it's a little bit of a, yeah. So web team, are you ready?
Yes, sir. You can start, sir.
Okay.
We are live.
Okay, apologies for this disruption in presentation of the seminar. You know, we live in difficult times, but it keeps us safe. You know, an antivirus can fix all problems which come via the wire. So I think in some ways we are good. Okay, I apologize for the delay, and we will begin the seminar now. Okay, dear friends, I'm Paritosh Pandya from the Computer Science Department, and on behalf of the Institute Colloquium Committee, it is my great pleasure to welcome you all to this colloquium by the eminent French scientist, Professor Gérard Berry. Gérard Berry is Professor Emeritus at Collège de France in it's a famous college in Paris, where he has occupied the chair on algorithms, languages, and machines till last year. Before that, he was the Chief Technology Officer at the Esterel Technologies, you know, and he has also been a researcher at École de Mines. Now, Professor Berry was recipient of the prestigious Gold Medal of CNRS in 2014. This is the highest French scientific award given each year to a single scientist among all disciplines. So, Professor Berry is a recipient of this very prestigious award. Coming to research work, Gérard Berry's research has addressed the formal development of programming languages for parallel and real-time programming. These languages are useful in high-level design of computer circuits and systems, and they facilitate formal verification. He is the creator of the highly innovative Esterel Synchronous programming language, and he's well known in the world of computer science, which deals with concurrency. Apart from his research work, through his courses, books, and conferences, Gérard has also been active in disseminating to a general audience the new algorithmic way of thinking and acting. Now, coming to today's talk, time is a key parameter against which evolution of system is recorded since time immemorial, if I may use such a word. In today's talk, Gérard Berry will explore the notion of time as it occurs in physics, computer science, and music. So I'm sure we are in for a treat. Please join me in welcoming Professor Gérard Berry with virtual clapping. And with this, I hand over the platform to Gérard.
I'm here.
Yeah.
I'm here.
So over to Gérard, and we look forward to his talk.
Okay, thank you, and sorry for the delay. When we change system, we have to do that the day before, otherwise nothing works.
Yeah.
Okay, so I will talk for time, from physics to informatics and music. This is a very broad subject, and explain first why it is a broad subject. Why do we discuss time and events in computing? Well, there are lots of real-time embedded systems everywhere, which are now better called cyber-physical systems, that is, systems that mix physics and informatics. System on chips, which drive your telephone and everything else, which are getting much more complicated than 20th century circuits. Simulation of physical systems, which is everywhere. A plane is simulated before it flies. And now they want to certify planes on the simulation and not on the actual plane. Simulation get very good. Worldwide time synchronization of computers, which is not a well-known subject, but it is absolutely essential. Time-aware databases, where elements in the database are tagged with time, and that's also very difficult because you need to synchronize all computers nicely to do that on a worldwide scale. Music, I will talk about that. Orchestration of web services, because web services become more and more complex. Web audio, which doesn't quite work right now because the internet doesn't know anything about time, which is a big problem, and so on. And also understanding our brain. I will just give a word about that because our brain is full of temporal things like oscillator, synchronization. For example, as soon as you start walking, you have a hertz wave in the whole of your brain that does a lot of things. Let's start with simple chips as an example. So this is a Motorola 68000, an old chip of simple. It's driven by a clock. You may know what it means or not. I will explain. 10 megahertz, it was very slow. The physics is simple, and power handling doesn't exist, dynamic power handling. Now chips are completely different. They are made of dozens or maybe hundreds of parts, which are called, interestingly, they are not called silicon parts, they are called IPs, intellectual properties, because they are assembled from parts, intellectual parts sold by many vendors like ARM and so on. Inside the chips, you have very complex networks, communication protocols, and extremely complex power management, because you want to reduce energy. For this, you reduce voltage, and you have to reduce the clocks as well to make the clock slower, and all of that dynamically, and any little bug in there kills the whole chip. And also, the chips are so complex that you need to simulate before they are built, and this is also very hard. Just for your knowledge, an iPhone modern chip or Samsung modern chip has about 12 to 15 billion transistors. So they are huge machines. Cyber-physical systems are the system that existed in the 20th century, but that you are now want to drive by computing. TVs, which are just computers now, cars, which did not change much shape, but totally changed inside, cameras, plane, and many, many other objects. So here, time is fundamental. When you press your pedal in your car, you expect the brakes to work in time and not whenever they want. So time is absolutely critical there. So in the 20th century, it was relatively easy to do that because there were local functionalities not connected to each other, like engine control or brakes, and they were clearly deterministic and uncorrelated with each other. Now it's not at all like that. You correlate everything in a car, in a plane, you couple suspension and brakes to better hold the road when you brake in a curve, for example. You go to automatic driving, which integrates everything. You couple with GPS, you couple with internet connection, web interfaces, and there are parts that should be deterministic for sure, some parts that don't care, and so on. So that get very complex systems. Thus, dealing with time and events becomes absolutely essential, but there is no provision for that in classical programming. For example, in C, in Java, in JavaScript, there is nothing real about time, and I will show you that you need to generalize the notion of time. And the background, the OS, predictive OS, threads, callbacks, event handler, all absolutely ignore time and cannot be changed into knowing about time easily. Oh, wait. So this is not good for the kind of application I mentioned. These problems are well analyzed by Edward Lee in Berkeley in 2 papers I show here. You get all the slides, by the way, plus more that I didn't show today. You get all of them in source format, you can steal them, and so on. So what we need to have models of time that we understand, logics to talk about time, languages to program with time, semantics to make a meaning to that, synthesis to generate programs, I mean classical C code or circuits, and formal verification for everything that concerns time. That's obviously a big program which has been out of the mainstream of computing that has chosen to completely ignore time. Good. How do we measure time? So the physics part of the talk. Well, there were clepsydra, there were solar clocks like the fantastic one, the e-Yantra Mandir in Jaipur. So that's me and my wife to give you the scale. It's 20 meter high, 27 meter high. It's a huge machine. And Delhi was the first place, Delhi was the first place where the time was unified in the whole district. Remember, this happened in the world only around 1900, that the unification of time existed. Beforehand, in French, we have 13 different times. Good. The major change has been coming to in the Dunstable church in 283, where somebody, who knows who, invented the escapement. So the escapement is here. The escapement is this mechanism here that makes tick-tack, 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 and is allowed to make the clocks regular. Invented that because clepsydra were freezing in England. Okay, it was then, so this is when time went from continuous to discrete. Very important step. Then when ships travel around the world, there was a big accident in 1707, and the Queen decided, and the Academy, the Royal Academy, decided to give a £20,000 prize to measure time. It took a long time, and in fact, it was done by a carpenter, John Harrison, who invented this chronometer that was able to shift no more than 1/3 of a second per day, which was totally fantastic. And but of course, since he was a carpenter, he was despised by scientists, and it's a long story. And you should read this long story in this fabulous book called Longitude by Dava Sobel, one of the best books I ever read in my life. In this story of measuring time. Good. Not having good measures is dangerous. For example, in 1853, one of the drivers of the two trains here on a single track had a late watch. There was no signaling. They relied on watch to know whether the track was free or full. And well, one of the driver had a late watch and 14 dead. And this is when they started to think about railway signaling, which is universal now. Railway signaling is all about time. Then there are progress. In France, we have the speaking clock. You could call the clock, which was a complex mechanism. And now that we have a speaking atomic clock, speaking with this woman and another man. And atomic clocks are becoming very common. You can even buy them for say, €1,000, and you get a very small clock, very late, which milliwatts, counts in milliwatts, even 10 less than that now. And the precision is in microseconds per day now. So tenths of microseconds per day. So you can be independent if you want on time. Thanks to the physicists. Also, the physicists know how to transport time using fiber optics and so on to synchronize. So now we need to program with time to understand it, so we need to speak about it. How do we do that? In the spoken language, there is nothing for that. It's fun, but it's not completely imprecise. For example, when you say we waited long minutes or long hours, what is a long minute? More than 60 seconds? Time passes fast. That's an interesting sentence. What is the speed of time? It should be given in seconds per second. So it's a pure number, 1.7. Makes no sense. Time passes faster and faster. You know that when you get older and older. So this is the acceleration of time, which is second minus 1 as a dimension. Makes no sense. So you know this is related to time perception in the brain, but not to science, not to computing. Good. Mathematicians have worked since long in the time, and this is Newton's notation. T is due to Newton, the T variable. So this is the arrow of time going from minus infinity to plus infinity, maybe, depending what you believe about the creation and the future. It may be cyclic, as in Indian mythology, or different. And you have events, and events are very important. In fact, you most often talk about events and not time. And you have a notion of simultaneity of dates on the real axis, and a notion of simultaneity having the same date. Good, but that doesn't quite work for us in computing. Why? There is no real numbers in informatics. There is no real number in nature either, according to physicists. So this is just an approximation which is useful, but raises too many problems. So you can also view discrete times where you have discrete instance. You can number in order, and you may place them on some hour of time if you need it, but not necessarily. And you have the same notion of events and similarity. This is not simple either because of Zeno. Zeno, the tortoise, you remember, the tortoise will never reach the goal because it has to Zeno says it has to perform infinitely many events in finite real time. But it's hard to understand this thing. It's not at all because the series converge as one hears. Not at all. But that's another story. So we need a richer view of time, which is based on two notions, precedence and causality, and not always in linear time, which is concrete or abstract. I will explain that in details. Local or share, we need to share time. So Einstein tells us it is impossible, but in practical life it is possible. It's not trivial, as you will see. Hierarchical and multiform time, that's my personal contribution, I think, to this. Regular or irregular, for example, in circuits, time used to be regular, now it's totally irregular. Exchangeable with space and so on, all of those things. So we want to specify, program, and verify with time and events. We need temporal languages and logics, and we need synthesis and verification algorithms to synthesize either chips or software, classical software enabled by classical computers. So we need to do very different from classical informatics. So one thing that is well known is temporal logic. Temporal logics are popular, and they were introduced long ago by and studied heavily by Knowley and many others. So look at a sentence we use in French: after rain comes fair weather. Why do we need temporal logics? Because if you put it in math, you say for all time t, reign of t implies there exists t prime strictly bigger than t, so that you have a fair weather at time t prime. You cannot sell this to anybody. It's just too complex, and t prime, I don't know why we have to name it. The saying doesn't name them. So you can write linear temporal logic, and with two operators, with instantaneous predicates, valid or not valid at any moment, and two operators, always and eventually. So this is, it is always true that if it's rain, then it will be eventually a fair weather. And this implication is not trivial. Is it a timing, sequence in time, or a causality? That's a good question for you. Does rain cause fair weather? Huh? Try to think of that. So causality is complicated. And if you looked at history books and debugging programs, I think you all have done that. You know the precedence, but you want to understand the causality, and that's immensely difficult. History is just about that. Good. So precedes is very clear as a notion if you have the arrow of time, and it's obviously transitive. Causality is much more complex. And maybe you don't have the arrow of time. So, for example, in history or in debugging of distributed systems, you have it only partially. You know the temporal relation, the precedence relation between some events, but not between others, like with the question marks here. And you have a causality sometimes, but there is an obvious question: is the causality transitive? And that's far from clear. There are good counterexamples. Like the causality transitive means A causes B, B causes C, implies, entails A causes C. Is that true? Ah, look at that. It rains implies I open my umbrella. Okay? I open my umbrella implies I'm dry. Can you deduce it rains, I'm dry? Certainly not. So the causality I used here is not transitive. There are many possible notions of causality. Some of them are transitive, some of them are not transitive. They are very hard to identify. So when you speak about causality, be shy. Try to understand that there are lots of notions of causality. I cannot explain the details here, but that's very important. Good. Let's take another saying in French: love ever, love forever. Very nice story. So if you are beginner in temporal logic, you would write, if I ever get in love, then I always get in love. This is not at all the same sentence, because this says, at the time I will fall in love, which will happen, if ever this happens, then From that time on, I will be always in love. That means you will be always in love with your first love. At the time it is your first love. That's not what you want to say. You probably want to say a little more complex, something like that. It is inevitable that if I love, oh yeah, this guarantees you will fall in love as well. But if I love, from that time on, I will be always in love. That's fine. But that means that if you love, you right away fall in love for your whole life. And that's not true either. So it's probably not the right saying again. So maybe better would be, if I in the future, if I love, then I will later be forever in love. It's not the same thing. Which one you want to say? The first thing is that when you write temporal logic, you have to think all about that, and it's extremely easy to make mistakes. But it's still, yeah, it doesn't tell you you are in love with the same person. Huh? But this is, I mean, you have to know that. If you use temporal logic, you have to know that. And it is difficult. There are all sorts of other temporal logic, like duration calculus, dear to Paritosh Pandya. And this is not an easy subject. It looks easy in the beginning. It's not easy when you use it. Good. Now I have a straight line for time, but no, that's not good. Time, when you do systems, we have two kinds of times. We have the past here, the past, which is linear, it's known, you cannot change anything. And you have the future here. In the future, you don't know it. So you keep making hypotheses about the future. You say, knowing that I done A, if I do B, I will get C. If I do D, I will get E. So linear is not very much, not excellent to express that. And maybe you needed other logics. And the main difference was shown by a wonderful example by Robin Milner, one of the great guys of informatics and a good friend. It's a difference between a British pragmatic and French crazy coughing machine. So the two coughing machines are the same. They have, you can put a coin and you have two buttons for coffee or tea, and you get coffee or tea. So the English machine is pragmatic. You put your coin, and then you can press either coffee or tea, and you get a bad coffee or a good tea because you're in England. In France, it's a strange machine. When you put your euro, only one the button will work. That is, the machine flips a coin and allows only one of the two buttons. So either you get good coffee or bad coffee, but you don't choose. The machine has chosen for you when you put a euro. Problem. Which one do you prefer? Everybody will say the English one. Yes, but in our logic, they are equivalent. Because the only sequences they can do is euro C coffee, euro T tea, and repeated. Aha. So can we distinguish between them? Yes. Using branching time temporal logic, this formula say it is always true on any path that if you put an euro, there is a path to coffee and there is a path to tea. Well, here I suppose the machine is dead after giving once a coffee or tea. If it loops back and comes back to the initial state, it gets more complicated. But essentially here you analyze potential future paths and not a single trajectory. And it's quite different. It's a very different logic. And they don't have the same computational properties, but there are systems for both. Both are useful. Knowing which one to choose is not a trivial problem. So logic are extremely useful, but not easy. Good. Aha. But the time is not conical for everybody. For example, there are lots of people in restaurants who hesitate to choose between X and Y because they think that if they take X, they will regret not having taken Y. You probably know people like that. So it's you have to make reasonings that had I known brings you back to changing the past. A prime would have been much better than A and so on. And you need to have this reasoning all the time. Why do you need it? Because we think in our brain, I don't know exactly why, we cannot think of time without referring ourselves constantly to a given present. We are not able to have a huge vision of time that takes into account everything at once. Our brain is against that. It's difficult to do. Good. Now let's go to more technical stuff. Vibration and synchrony. This is the key thing for whatever I will say next. As I said, in the 20th century chips, everything was simple. So how do they work, the chips? Well, it's very simple. You have wires and gate, and you put voltages, 0.5 volts at the time, for example. And here red will be 5 volts and Y is 0 volt. And then the voltages, you put them and you keep them constant at the inputs. And here you have gates. So that's a XOR gate. These are AND gate, and this is an OR gate. And this will build an adder for 3 bits with a sum here, a sum and a carry. Good. So what happens is that the electrical front propagates in, which is different from the electrons. Huh? The electrical front propagates on wires at the speed of light, roughly, not quite, but almost. And then the gates compute, and they take variable times. They don't take all the same times. For example, you can get the sum right away, but you have to wait a little more for getting a part of the carry, another part of the carry. And here you have a 1 coming to the carry, so you can get the carry right away, even if the third component has not yet been computed. And when the third component is computed, it cannot change the result. That's very important. It cannot change the result. Good. So what's happening is that there is a wavefront propagation in wires and gates. And after a while, if you keep the input constant, the outputs become constant. And this is the key to anything. And the important thing is that in the circuit, there is what is called a critical path. The critical path is a path that if you stabilize this path, you are sure that all the other paths are stabilized. It's the path of maximal delay, knowing that the delay depends on the actual delay, depends on the temperature, pressure, and so on. So when you say your Motorola chip runs 10 kilohertz, 10 megahertz, it means it takes 1/10 of a microsecond to stabilize. If it is 1 gigahertz, it says 1 picosecond. Good. This is magic. Why is it magic? Because now you have two views of circuits, and this is what makes this industry possible. The view of circuit electrical propagation is the view of Boolean equation. So you write this kind of Boolean equation here to define the sum and the carry. In Boolean equation, you have no time at all. This is why they are much simpler. You can use Boolean algebra. And this stabilization in finite time means that if you wait long enough, you can pretend everything is as if you had no time. And this is the main idea in the sequel. So this is a fantastic idea because it transforms continuous into discrete in a very neat way. This is why most circuits are synchronous. There are also some asynchronous circuits, but not that much. So remember that waiting for critical delay is solving the equation. A circuit is a parallel vibratory machine that magically solves parallel synchronous equations. Good. So what you do, in fact, is to replace logical time, the Boolean time, if you want, Boolean, when you solve equation, there is no times, into physical time, and it works as soon as there is no overlap between inputs and outputs. You don't change the inputs before getting the output. And this is why circuits have limited frequency that depend on the voltage. This becomes much more complicated in modern circuits because you change the voltage, so the critical time change, and you have to be very careful in what you do in these circuits. Good. The same for music, exactly the same. You go to a concert. Here is a Western concert. It's the same with tabla and sitar. Huh? So you have several musicians, and they listen to each other. They look to each other at speed of light. They listen to each other at speed of sound. If they are close enough, the speed of sound can be neglected. Okay? So, and if you are in the room, you neglect the sound difference between the instruments because your brain is not able to distinguish two sounds that were more than 20 milliseconds apart. And the same when you generate sound by computers, if you generate note by less than 20 milliseconds apart, they look simultaneous. So you again have two things: vibration in the room. Acousticians deal with sound propagation, just as electronics people deal with electricity propagation. But musicians and spectators neglect the speed of sound, exactly as circuit designers, logic circuit designers work at Boolean level and neglect the speed inside the circuit. Because the electronics people tell us, I can make it slow enough so that it works. This is fantastic. Good. So that works only if the room is small enough. If you have a big orchestra with, say, hundreds of musicians, there are pieces like that, it doesn't work because the musicians are too far from each other. And if they are 30 meters, which happens, it's a tenth of a second. It's too much, clearly too much. So you need the conductor. What is the role of the conductor? Is to synchronize the musician with light instead of sound. Seeing the conductor is much faster than hearing your neighbor. This is why conductors are needed. Good. So now another idea, absolutely fundamental to me and dear to me, multiform time and clock hierarchies. So assume you are running in a stadium, which you do every morning, of course. And when you run, what are the time units? Of course, you have a second. Of course, you have an hour. That's classical time. You have a more stranger thing like the morning. I told you should do that every morning. But the morning is not regular. It changes every day. So it's an event which is not aligned to seconds. But it's an event. It's perfectly respectable as a time unit. You say every 3 mornings, no problem. You have meters. There is no difference between seconds and measures when you run. You can say, for example, run for 10 seconds or run for 10 meters. Okay, the same sentence. Not with the arrow not with the classical Newton time. Huh? You have laps, which are maybe 400 meters. You have steps. You can run for 10 steps. Steps are independent of meter a second. You have heartbeats, which are independent of the rest. And all of this, they define their own unit of time. It's not second, but it's just homogeneous to second. And you have heart attacks, stroke, that you want to avoid is the absence of heartbeat. But heart attacks are rarer, but you can count in the number of heart attacks. I remember when I got the time I got my second heart attack, which is not something I wish for you. So how to master a language is about programming with that. So here is the program to run every morning. So run it's a joke because run is a keyword in the language, say execute the slowly behavior that can be very complicated. So you program only with time. So you run slowly. This would be infinite. So you have to bound it. How long do you want to run? 100 meters. I don't tell in seconds. You run slowly for 100 meters, which is the perfect unit of time. In general, as view of time, of course. So, okay, that's fine. That program lasts exactly 13 meters, 100 meters. Now, after that, during 15 seconds, you jump and breathe every step. And jumping and breathing can synchronize on heartbeats. Maybe there are complex things that synchronize. And here you see this is parallel programming. But it is synchronous parallel, not like a synchronous programmer with threads, which is uncontrollable. Synchronous programming is perfectly controllable, as you will see. Good. So the important thing is abort. Abort tells you when you want to specify the duration of something, you just run it and kill it. Killing is more important than starting. In fact, all the Hindu gods are there. You use Brahma to start an activity. You use Vishnu to maintain it, and you use Shiva to kill it after 100 meters. And we synthesize circuits out of that, and we call the wire inside the circuit Brahma, Shiva, and Vishnu, the control wire of the temporal policy. Good. So what is the duration of this program? It's 100 meters plus 15 seconds, which makes perfect sense. Now you go on full speed after that. This was the beginning of the training. Go full speed, but not infinitely. When do you stop full speed? Well, you do that every lap. You stop at the end of the lap and you redo that every lap. So this is just as you speak. Totally different from C or JavaScript or anything else. Now you limit all the stuff to 4 laps, and maybe you go to shower after that. Good. It's fine. So what is the semantics? Oh, you do, sorry, I forgot to say, you do that every morning, of course. The semantics, to give the semantics, we just assume, as in a circuit, that the internal delays don't matter. So that all control operations take no time relative to meters, steps, seconds, laps, and so on. Cool. That makes a beautiful mathematical semantics, which is used to drive the compiler, the circuit synthesis, and so on. But think, there are dangerous parts. This part here, sorry, I have to go back. This part here, jump and breathe, is dangerous and can kill you if you are careful. So you need to monitor your heart. So in parallel, during that time, and only during that time, you monitor your heart, and you say exit heart attack, which is a trap. It's just an exception if you want. And then you handle this trap by rushing to hospital. And this cannot exist in Java, for example, or any other parallel language, a synchronous parallel, because it will kill in 0 time all the parallel activities, which you cannot do with threads or processes. Good, so all of that makes sense. Fine, to implement that, we either generate circuit of software, and we build a cycle execution model exactly as for circuits, with a critical path and so on. The 4 cycles, wait, here, read inputs, computer action that generate outputs. And the key thing is to ensure that there is no competition between cycles. That each cycle it gets in order. And this is the way all the airplanes are programmed now. For example, the airplanes, the trains, the cars, they are all done with that. And you call synchronous or zero delay or simultaneous everything that happens within the same cycle, even if it is complex, like propagation of electric circuits. So, as I say, we can generate either circuits or super fast circuits. I mean, the runner, you execute that in maybe 1 gigahertz is too easy, but it's no useful too. And in software, the same. So that's very interesting. And in fact, we start from concurrent programs. We resolve concurrency at compile time to generate race C code, for example, or concurrent circuit, because electricity is concurrent. It's deterministic, unlike asynchronous concurrent programming. There is no interference between input, output, and computation, and there is timing predictability. So now it's an industrial product, major from Stereo Technology, the company I co-founded. And this is the new view. It's called State 6, which is a mixture of state charge-like things and continuous control with data flow coming from the Lustre functional language. And it's all a functional language. And this is a major tool because, for example, all Airbus airplanes are programmed. All the software, the huge software of Airbus airplane is programmed with that. And for example, there are formal verification of the huge airplane control software, which is a count when compiled in hundreds of thousands of C line. There is a proof, for example, that it cannot have runtime errors, and there are automatic computation of worst-case execution time. Good. This is industrial. It's not anymore research. Good. Let's go to simulation. Another very interesting thing. There are lots of systems to simulate temporal behaviors, like Simulink, Modelica, and many others. So, for example, you can have this simulation. You have a ball. You want to start it, hit a ball that will hit the wall, bounce back the first ball. So the equations are the linear differential equation, very simple. You find that in the bottom of the slide here. Oops, sorry, these are, and there are things to define shocks and action on shocks, which is to revert the speed when to exchange the speed when the ball meet, or to revert the speed when the ball hit the wall. That's fine. So if you launch Simulink or Modelica, it's good. What you see is what you expect. Very good. Now, put the second ball stuck to the wall. Now, if you Simulink and Modelica tell you, oof, I don't know what will happen, because they compute by integration, and here they don't know what will happen after this shock. They have to move the ball. So there is a big risk, and it often happens in this simulator, that instead of being a nice simulation that just sends the back bouncing back, does this, which is not exactly what you want, and which is not what the physical system does. So the real bad solution is to say, oh, but we didn't take care of elasticity. There you will go nowhere, because you will do extremely complicated things to deal with an extremely simple problem that you can ignore electricity, which is what the Newtonian mechanics does, for good reasons. Good. The solution is beautiful. It has been done by Marc Pouzet, Tim Bourque, Albert Benveniste, and Benoît Caillot in France, is to replace the real numbers you use for simulation, or the floating point numbers, by non-standard constructive analysis. And the idea of non-standard analysis, introduced by Robinson in the, I don't remember, 50s or 70s, I don't remember, beautiful mathematical theory, axiomatic, tells, usually you say epsilon when you do analysis, you say epsilon is a small number. How small doesn't make sense. So the idea of non-standard arithmetic is to introduce a new algebra of infinitely small numbers. So 2 epsilon is bigger than epsilon, but any n times epsilon is smaller than any real number. And you have a lot of infinitesimals around each number. And if you do that, you can make the semantics absolutely okay, because what's happening is in no time, this ball will hit this ball. In no time, this ball will hit the wall. In no time, it will bounce. And in no time, it will chase the other ball, which is written here. This is the causal scheme of this reaction here. And you cannot do that if you integrate with epsilon non-zero. But if you say, oh, now we have changed to infinitesimal mode, you are not integrating anymore. You are dealing with finite automata and things like that. And so what they do in the language is to add a type checker on the equation that will type check when things should take time, that is, be integrated with integration schemes, or when they are instantaneous, as they should be dealt in the infinitesimal world or in the automata world. And this is now, this is a very beautiful solution, which is, for example, embedded in the new version of the tools at SL Technology, and they want to use it in Modelica as well. But Simulink is harder because there are millions of users, and when you change the semantics, nothing works. Even the semantics was wrong, you know that. Good. So if you do that, the behavior is what you expect. Fine. Now let me go to the last part of the talk, music. It's not all music. I'm not talking about Indian music, which is vastly different. But Paritosh and myself would like to work on Indian music as well. I'm a big fan of Indian music. I've been to lots of concerts in India, and just extraordinary. Here I talk about composed music, which on the contrary of Indian music is made to be replayed over time. But replayed with freedom. That is, you don't tell exactly which millisecond things should be played at all. So you write scores. So the first scores were very rudimentary. If you look at that, scores of 1600, say, you have notes, you have duration. So a black is duration 1, a white is duration 2, this is duration 4, this is duration 1/2, both of them. You have duration, which is binary in general, but can be ternary as well. And that's all. You have no measure bar here. It's a flow. So the duration are specified duration, but they are not meant to be real-time duration, because you want the interpreter to have freedom of organizing the tempo, the duration, the articulation, the enhancements, whatever. That's the same in music. The ALAP has no fixed notion of duration. After that, yes, when the tabla comes in, it's much more regular. But still, you are never, you can be, for example, in jazz, you are never on the beat. The battery is on the beat. The drums are on the beat, but the musicians are never on the beat. So it's very clever. Music is very clever. So there is nothing, there is no indication of how to play this thing here. So, but it shows already that writing music is playing music. You write with a conceptual trend in music, and you play just like modern circuits, the clock changes over time. You play with your own clock that changes over time. Good. Bach, for example, is different in the 1700. It's different. You see, for example, here you see there are bars, vertical bars, like here, that cuts into phrases. So say 4 beats in a measure, and so on. But if you look at Bach, there is not even for which instrument it is written. No indication about how fast it should be played. No indication about orchestration, about how to articulate, about how to phrase the music. Should it play regular or irregular? This is to the freedom of the interpreter. So written music is not composed music 100%, is to the freedom of the interpreter. Later on, romantic music, like here, Symphony by Mahler, there are more indications. First, the instruments are indicated here, and then the tempo, sehr langsam, very slow, which doesn't mean very much. And then a tempo, molto ritornito, which means you slow down a lot. And a tempo, you come back to very slow, which is not defined. Molto adagio, no, you don't come back to there, you come to molto adagio. It's quite imprecise. And of course, conductors and musicians can play that very differently without changing the music too much, okay? And here you say, piano, piano, pianissimo subito. It's all in Italian, of course. And this is also something that is left to the interpreter. More interestingly, you don't have only beats in music. You have themes, and you have repetition of themes, and you have constructs and moods and whatever. So this is one of the pieces that has changed the 20th century, Stravinsky's symphonies for wind instruments. And you see, in fact, you see here several parts. This is the audiogram cut into slices corresponding to repetitions of the same motifs, the yellow and the same beats. So there are 3 beats here, 164, 128, and 192, and they alternate, and there are patterns that are, so the patterns that repeat are not the matter when you run. They are not seconds, but they are patterns. So it's again multiform time. In the music, you have lots of time. Repetition of the first theme, coming of the second theme, repetition of the second theme, recalling the theme of the previous movement, and so on. So it's just multiform time as in SRL. Good. More interesting. In the 20th century beginning, there was only musicians playing on stage. Now we can do everything with electronics. Electronics is a bad word. With software. It used to be electronics, now it's all software. There are only 2 electronic parts, the encoder and decoder. So in the 20th century, in the 70s, for example, or 50s, people made electronic music and on tapes, or Mac tapes, on computers, and they played it with human beings, so dialogues. But it's not quite a dialogue, because electronic music was played with a musical feeling of a tape recorder or of a computer, which means nothing. So it was as specified by the composer, no freedom. And so the conductor had to adapt to the electronics. And that was a big problem for musicians who would not express themselves as they wish. So there has been a fantastic invention called Anteskofo by an Iranian guy named Archiakont, which is a score follower. This thing is hard, and it uses AI, smart AI algorithms. What it does is that it knows the score as well as the musician, so it knows the score. There is a microphone, for example, on the first violin, and it will follow the score in real time. It will detect all the events played by the first violin and compute dynamically the tempo and the tempo variation of the first violin. This is very smart, which means that now you can adjust the software or electronic music to the musicians instead of doing the converse. And you can also use notes by the musician to start new music that had been programmed to start only when this note or this kind of mood appears. So you can do analysis of how the musician plays to determine what will be played by the music. Furthermore, you have a problem. How do you write score for a computer, knowing that a computer can do everything? Every sound, every sequence of sound can be programmed. How do you write a score? People try to have notation and so on, and like that, with levels, with all sorts of things. But these notations are never perennial. They are often meant for one play, one work, or maybe 3 or 4 works, and they disappear. Nobody knows how to replace them really, and so that this is not correct. So what we say now is that score should be a program, an algorithmic score. And you can also add sound spatialization, because now you can do 3D in audio, and it's used heavily. And so what is a modern score for a computer that can do everything is an absolutely fantastic, completely open problem, which doesn't quite exist in Indian music, but maybe there are equivalent problems. So this application is now on, oh yeah, there is another invention here, is that there is what is called the phase vocoder. For example, on your telephone, it's called Metronotes, not on Tescofo. On your telephone, iPhone for the time being, but also Android soon, you can say, for example, I want the score of a Mozart concerto for piano, and together comes a record of the Paris Orchestra playing the orchestra part. And so you can play the piano, and the orchestra will play with you, it will follow you. You can train slowly on an allegro, and the orchestra will play slowly, but it will keep exactly the same sound, even slowly. This is another major invention, phase vocoder, which allows you to stretch in time, accelerate or slow down a recorded sound without changing the spirit of the sound. This is fantastic. So Metronote, okay, like a metro and note like internote, is available on. It's a fantastic system. I use it personally. I play flute, and I don't have a harpsichord with me, and no harpsichord player. So now I have an harpsichord in my computer that follows me when I play. Good. Here are, for example, inspired from Esterel, translation of thing. You see loop adds instead of rewriting the same thing, putting a loop adds a lot. This is a very simple example. There are other things, for example, and Tescofo is very good at that. For example, recovering mistakes. The computer makes mistakes in listening to sound. The music can be very hard, so the violinist may make mistakes too. And the mistake recovering is essential because the show must go on. You cannot say, the computer cannot say, I don't know what to do during a play. So that's very hard stuff and fantastic. So to finish, I would say there are lots of work in progress, like mixing continuous time and discrete time, which I had no time to talk about. I made 2 years of courses at Collège de France on that. Mixing synchronous and asynchronous frameworks for semantics. Relaxing determinism and predictability to be good enough. There are all sorts of things in elastic circuits, in a GAL system, in web-based system control. Improving music score, I told that. And all of that requires to think much more about time than usual. And I hope I helped to do that. Conclusion, there are 2 opposite ways to build systems. Hack them, test them, and hope they work, which is 99% of the applications. Think about them and use well-defined tools, which is hopefully used in high security things like airplanes, not yet in cars because nobody cares. and certified system. It's universal. SRL technology has more than 300 customers all over the world in heavy industry, cranes, for example, or ships, or trains, or some cars, airplanes, all airplanes now, I think. Synchronous languages are SRL from a very strong basis. They have a beautiful mathematical semantics worked out in 20 years. It was not a simple game. And the principles I showed extend well to other things, to continuous discrete modeling, to web-based control. SRL has been transformed into a super layer of JavaScript now as well, so I can use it on the web. It's called hip hop. That's it. And sorry, this is the end of my talk. Thank you. I hope you liked it. Are you here?
Audience, I'm sure you'll join me in clapping for the speaker for a very interesting talk before we begin with the questions and answers. So here is some.
Could you hear it? Could you hear it now?
Yeah.
Yeah, the sound was okay?
Yes, it was fine.
Okay,
so
good.
I think we had a very interesting talk, and we should thank the speaker for that. We would have, I know we are running a little behind, but we would have time for some questions. So if you have a question, kindly unmute your microphone and your camera, and please ask your question. Thank you. Feel free to ask whatever questions you have to the speaker.
Can I ask a question? This is Sriram here.
Yes, please. Sriram.
Hi. So thank you, Gérard. This was a really lovely talk. So if a conventional language like Java or C were to be equipped with a sense of time, if time were built in to a conventional language, what would you expect would be the change in the way we develop conventional systems like, say, operating systems or databases and things like that? How will given that time is baked in, what kind of errors would you expect to go away, or what kind of facilities would we be able to develop? I mean, I imagine that concurrency would be an easier thing to reason about.
Concurrency makes life much easier. This is sure. If you suppress concurrency for SRL, it becomes the same nightmare as with any other language. Although you have sequencing, but you need three things: sequencing, concurrency, and preemption. Preemption is abort and every and so on. If you remove one of these three things, you're dead.
So
for example, no, except in some application. But in C, you have none.
So in the examples, I'm sorry, please go ahead.
No, people have tried to augment, because they want to keep the same syntax, maybe. They have wanted to augment languages with reactivity IDs. And this has been done for C in a very bad way, I think, to me, by CEU in Brazil. And parallel is not commutative, which is leading to a nightmare. Reactive ML is an interesting thing where it extends CAML, but it's not real time. It's not reactive, in fact. It computes like SRL, but it doesn't react. Because, for example, you cannot react to the negation of an event not being there. It's not possible. So there are compromises to be taken, which I don't like. So the solution we took was immediate. SRL translates into C, for example, but straight C. And we guarantee that the behavior isn't changed. That's the way all our planes are programmed. Okay. You can do better. For example, we did an extension of JavaScript, which works as follows. JavaScript is extremely good for us because execution of JavaScript is atomic. So we have a hip-hop is a thing that extends asynchrony of JavaScript by allowing to make it makes many things, but it allows you to write the server and the client in the same code, and the distribution will be automatic, and data exchange will be automatic. And we added on top of that a reactivity layer to deal with complex reactive behavior, which is called hip-hop, which doesn't use the same syntax. It uses the same syntactic frame, I mean brackets and so on. But it builds modules which are exactly like SRL, in fact, and then that are compiled into JavaScript and executed at runtime into JavaScript. So the look and feel, and they are mixable with JavaScript arbitrarily. So that's, I think, a very good solution. It was presented at PLDI this year in March. There are other attempts, but I think all attempts to put that in there was an attempt in Berkeley with ECL, STRL-C language, but you have too many restrictions. There is a very nice attempt, however, in Kiel called SCL, which is a little more clever than STRL in relaxing constraints that STRL obeys. So SCL by Reinhard von Hanstetten and his team is very interesting. And his ideas are really good, the best successors I know of our ideas, and they are better.
Thank you. I'll check out both hip hop and SCL.
Yeah. It's if you want to just to patch Cino, it's too different. But you can do clever stuff.
Okay, thank you. Thank you, Sriram. If there are other questions.
Just say this note with the last 2 hours. So here you have a very nice place for freedom. But if you depend, for example, when you launch a satellite, the time control is very precise. You know about relativity, you know about everything. You have GPS, you have you have atomic clocks, you have everything. So it's a very broad class of applications, but there are many things that are not there. Sure.
Thank you. Yeah.
Paritosh, I have a question.
Avi, please go ahead.
Gérard, I've always wondered that the best technology, even though it exists, does not escape into the world to influence large numbers of people. When you say that there are 300 customers for STL technologies, right? I'm wondering why that number is not 1,000 times more. What is the problem that technology like this, which is, building safety critical systems is a very important activity. In fact, all our systems are essentially safety critical in some way or the other. I'd like to ask you about what are the difficulties of exporting these ideas into industry, into the world out there, into conventional teaching?
That's a very good question. The most companies want to hire fast, lightly trained engineers. For example, in automotive, it has been like that for long. Many industries are based on mechanics. I know very well Renault and Peugeot, for example. And when we went there, they said, computing is not important. Now they say the contrary, because they realize that their car is dominated by Bosch and not by them. So Bosch works with classical techniques, but nobody complains. So they have no requirement. They have strictly no requirement from the state so that their program works. Medical applications, there are basically no requirements. So when you have no requirements, you do cheap. When you have requirements, you don't do cheap. So there are two kinds of requirements. The official ones, certification, and the non-official ones, the cost of accidents. So you may know that Toyota has killed 89% because of the totally buggy engine control software. 700 pages of analysis showing how buggy, you cannot save it. It's completely rotten. Nobody cares. Nobody complains. Well, Toyota has lost $2.1 billion just for that. Nobody complains, nobody knows the story. So that's one of the reasons. I don't know how they do now. Some people do well. For example, trucks have certification, unlike cars, and they use this kind of technology. They are much more serious. For cranes are very dangerous. Harbor cranes lift 1,000 tons, you see, so it's all software. Huh? It's all driven by software. They use this kind of technology. Trains, they use this kind of technology. Maybe you know that the first subway in the world to be completely automatic was the Paris one. And do you know that the software has never been tested? Never been tested. It has been proved before. Nobody has been told no test and no bug in this history. So you cannot convince people that can work cheap. This is true everywhere. But when I say 300 companies, it's almost all the companies that don't work cheap. Hey.
Okay. So say, Gérard, if you were to train 1,000 people in STRL skills, would you be able to have them absorbed?
Well, first, I wouldn't use a STRL bus case. They do that. I mean, there are lots of people using it, but there are, you know, for example, computer scientists think of programming as a C.
Yes.
The people who do these control systems, they are mostly control theory people. They think like programming like control theory. And going from control theory to scale to C is very hard. Going from control theory to scale is trivial. It's the same formalism. It's block diagrams. Okay, for them, there is no change. For example, and that's important. It's not the same population of programmers to do that. The only thing that may change the thing is regulation, to me. That is, for example, in medicine, I don't know if you read the paper about pacemakers. Two researchers have studied pacemakers, and they have found thousands of security bugs in them, just by trying stupidly. And they discovered that nobody in the pacemaker industry knew about that, knew about security bugs. So the Internet of Objects, the IoT, will be a very big problem, because in the IoT, I use IoT objects, they are totally stupidly done. I mean, they have no security whatsoever. Admin, the password. Everything is like that. So this flies because they don't exist yet. But if they exist, if people realize that cars should be better, now they start realizing it will be different. Only external pressure can make people use good technology. That's true everywhere. Everywhere.
So you're saying that only if failure becomes too expensive to ignore will things change? Not even.
Big failures are not expensive as soon as they remain unknown. $2.5 billion for Toyota is not the problem. The problem is that it has been made public. Big failures exist everywhere. You know, in security, I know one company in France that got NotPetya, they lost, and they admitted they lost 200 million euros in one morning. Okay, they made it public. But I know that many people didn't make it public. And these people won't change.
So I won't hog the conversation here. This is a conversation that Paritosh and I want to have with you separately. But this is very important conversation to have.
No, it's very important. Therefore, training people is very important, because somehow what you cannot tell, I saw that yesterday, you can never convince somebody to stop smoking because it's dangerous. That doesn't work.
Yeah.
People get convinced too late. So regulation is another way to do that. You know, where to put the energy. I think has completely stopped to do is to try to convince people who do not want to be convinced. Step one. And step two, when you talk to research departments of companies, be careful. It's very often the best way to be rejected by production. But that's a big deal, because if you talk to research, if you don't talk to research, you cannot talk to production. If you talk to research, because in many companies production hates research, you may. So I totally gave the idea of trying to convince people who will never been convinced.
So Kavi,
That's
on
sending energy to slash null.
Yes.
on that slightly pessimistic note, we should defer that conversation later. I know we started late. We have overshot. Maybe there will be time for one more question. But while people think of that, let me ask one. On one of your slides, you had a list of very nice open problems and problems for further work. One of them was things like mixing asynchrony and synchrony. I know Professor Shamsundar is in the room. You have worked on that with him at IIT Bombay and TIFR. My question is, you say you have lectures on those topics, very interesting topics. Can you point to where we can find your lectures or material on those topics?
Oh yes, the lectures were done in French, but at that time I guess they were still translated in English. But on the site of Collège de France, on my site at Collège de France, the videos are available with English dubbing. But the problem is that the dubber did not take any second with me to understand the vocabulary. So it may be very nice to hear, very fun sometimes. Like for example, if you say a semaphore in synchronous programming, it will be translated to a traffic light. Okay. But no, I can send you. What I can do is to share all the material I have developed so far, all the transparency I've developed so far, because including in the English version, I gave talks at, for example, at the Mark Tobordov PhD schools on that, fairly extensive, and I can share whatever you like. I mean,
please, that would be very nice, and we'll make sure it's available, to the audience.
Yeah, and we can discuss as much as we want. I mean, these are deep questions. I'm not the only one to say that. There's a fair large number of groups in the world, and the Berkeley group is very good, and the Kiel group is very good, and so on. Yeah.
Okay. Thank you very much.
These are non-trivial. But I thought a question on matter and time in the flow of questions.
Right. If there are no more questions, if there is one, quickly ask one. Otherwise,
there's a question in the chat.
I should see the chat. Yes, you are right. In the chat, there are two questions. There was a point in one of the slides saying meter as a unit of time, but something has to be a unit. To be unit, it has to be uniform, right? And change in speed would change the time measured in meters, right?
No, exactly not. So to be uniform, nobody knows even if time is uniform. It's just a guess. We call it uniform, but it doesn't mean anything. No. Matter is a unit, is a uniform unit in terms of matter, and time is not a uniform unit in terms of matter. Each unit is uniform in its own sense, and all the others become non-uniform in this sense. So it's just like in relativity, simpler. It's just like in relativity. There is no universal time in nature. Everybody has a time. If you move fast compared to somebody else, you don't have the same time. So uniform time, you should just get rid of this idea altogether, which Einstein did in 1915. But even for second and matter is the same. So that's quite. So the speed depends whether you measure the speed in meter per seconds or in seconds per meter. Both are valid. You can say, I take 3 seconds to do this measure, and seen from the speed unit, it's a speed in seconds per meter. Perfectly valid. So it's you have to be flexible. Whenever you talk about one unit like matter, you see the other unit as other units, and you can discuss between units, but there is no reason in systems. The time is often particular because of mechanics. But for example, I've written many STL programs in which there is no time at all, and they are very nice, and that's it.
Thank you so much, sir. That was a beautiful answer.
Yeah, that question was by Arjun Sadananda. There is another question by another Arjun Bhattacharya, and he has a question that there is this report in the newspaper that researchers from several institutes collaborated in some quantum computer and returned the state of quantum computer a fraction of second into the past.
Would you know what that sentence may mean? Because I don't know. I know a little bit quantum computing because my head at Collège de France used to be Serge Haroche, who is the guy who got the Nobel Prize by building a Schrödinger cat, which was thought impossible. So he got the 2012. So which means the state of a quantum computer. I don't know what that is. I mean, you have to define the state. There is no simple notion of state in a quantum computer because it's entanglement. So I don't know what this sentence says. I don't know the paper. I'm not very confident on a newspaper to tell things about quantum computing, but I don't know. I have to look at that and ask my quantum friends. I don't know. Never heard of that. Nobody knows. We assume that time is irreversible, but there is no proof of that. That's for sure. And if you will read Penrose, who just got the Nobel Prize in Physics, you will see that his notion of time is very interesting, with multiple worlds, as in the Hindu, and that you can have traces of before the Big Bang in the Big Bang, and so on. But this thing, I don't know. For a curved space-time, how can one define time? You need to generalize relativity theory. It looks hard, but it's not that hard. Calculations are very hard, but the principles are not hard. There is one time per point in the universe, per moving point in the universe, sorry, and that's all. And you cannot, in relativity, you cannot synchronize times between 2 points unless they are at the same place. So curved space-time is no problem. It's a curved space-time. You define time as you define space, in fact. Don't keep your usual intuition when you talk about quantum and you talk about general relativity. It doesn't work at all. It's a proof that your intuition is wrong, which is standard.
Thank you. So I think in favor of keeping time, we will close the question answer part of the session, but we've had these interesting questions. Let's once again thank the speaker. On the behalf of the Institute Colloquium Committee, also, I would like to thank the speaker for accepting this invitation and for allowing us to put up this talk on the web so that it is available as a resource for us and for others to follow. So thank you, Gérard, for a lovely talk.
Thank you all.
Many more talks.
Thank you.
Thank you all.
I think your old colleague Sundar is in the audience.
Have a good day. Bye-bye.
Bye, everybody.
Hi, Oliver. Bye. Yeah.